Okay, all right. Hi, everyone. I see that there is enough people, so I'll just go ahead because I have half an hour to do my presentation. Feel free to write in the QA section, and I'll see after the presentation. I'll try to answer those. So my topic for today is control auto-tuning for multi-copter and fixed-wing vehicles. That's been a project I was working on for the last few months for Auterion. And I have the pleasure to be here to share that with you. It's something that will be in PX4 for everyone, so don't worry. It's not anything proprietary, and you'll all be able to test it in the next few months. I'll start first to present myself. So my name is Mathieu. I'm an employee of Auterion for 3 years now. I'm working with PX4 for 4.5 years. And I'm doing control system software and estimation also for Auterion now. And let's start the presentation. So basically today I'll start with a bit of control theory, such that everyone is up to date and can follow the presentation. It will be a bit technical, but not too much, so that everyone can follow it also. I'll start to introduce the block diagram for control theory we use, some control tuning techniques. Then I'll motivate why we need auto-tuning for our drones. And I'll start to show where it comes from. So it really comes from adaptive control, and why I choose that approach for auto-tuning. Then exactly I'll start to detail a bit which pieces I choose for PX4 to implement. Some Python prototyping I used to develop the algorithm and to test it. And then some detail about the implementation on PX4 and some flight results. So first, hopefully you can see my pointer here. I'll just make sure everyone can see the pointer. Yes. Okay. So basically, in control theory, we have block diagrams like that. And for example, here there is vehicle dynamics, which represent the mathematical and physical model of your vehicle. Take some input, some forces, output some angular rotation, and things like that. And that's basically a control loop that we have in the drone. So we have the rate control loop. So we try to control the angular velocity of the drone. And then we have the attitude loop around. So what we do here is that we measure the behavior of the drone with some gyroscope. We try to control the angular rate here with a rate controller. And the same for the attitude. We also have an attitude controller. And we need to tune those. So those controllers have some parameter inside, and you need to tune them for each drone you have. So it will be different if you have a large drone, which is a multi-copter, a large one, a small one, or if you have a fixed wing. The structure is the same, but the parameters that are inside are different. So we have to find them. A bit on control tuning now. So you have different type of controller and different ways of tuning your controller. So the most widely used one in industry is called PID. It's proportional integral derivative controller. It's quite easy. It's kind of intuitive to tune also. And there are many different approaches to tune it. So there is one approach, which is just manual tuning that requires some experience. You try to increase, decrease some gains manually, and you basically feel and see the behavior, and then you try to adjust that manually. It takes a lot of time, but it usually works for most processes. You have other techniques like Ziegler-Nichols, which is you have to introduce an oscillation in the loop to try to find some characteristics, and that's obviously, for example, too dangerous for aircraft because it could just crash your drone. And you have here another one that I'll explain, which is auto-tuning, which is also a non-model based, but at the same time, you don't really need the model to give it to the system. You don't need to to identify it yourself, but the system will do it for itself. So the auto-tuning algorithm will estimate a model and design the control for you. And you have other methods that you can use if you have the model, the physical model of your craft. You can use loop shaping, edge infinity. That's some method that you usually use in academia or research project, but there are not so much used in the industry because it's a bit complicated. You need a control system engineer to use them, and it's a bit more complicated. And often just manual PID tuning works, or in our case, auto tuning works as well. So why do you need auto tuning? So as I said, for manual tuning, you need someone that can fly drone, usually also someone that can fly drone in acro mode, so it's just angular rate control. It's kind of complicated, especially if it's not tuned already. Usually need a second person to update the gains for you. It's kind of dangerous because you have to do it while flying. So if you do a mistake, it can lead immediately to a crash. You need to understand also what you have to tune. So for PID, it's fine. You only have 3 parameters. It could be a bit complicated at first, but as you get more experience, it gets easier, but still it always takes some time. And if you need to do a new bring up, for example, you have a new copter, you have to redo it yourself. And if you don't know how to do it, you probably need to hire a control system engineer that has some flight experience as well. It takes a lot of time, iterations to achieve a good and decent tuning. And also, every pilot has his own standard. So if it feels great for one pilot, maybe another one will like to change a bit the tuning and is maybe not fully happy with that. And also, you're really limited to simple controls because if it's a bit more complicated than just 3 parameters, it's basically impossible to do it by hand. And then here, the auto-tuning on the opposite side can be used by everyone, so you just need to click on a button. It will do it for you. It's much safer. You only have a few parameters that are really high level. For example, what's the responsiveness you want to have? What's the rise time, for example? So it's really the final objective of the closed loop systems that you need to specify, and not just a parameter that is almost meaningless for you. You don't need tuning experience. It's also fairly fast. It's usually you only need a few minutes to complete it, and it provides usually a good, at least base tuning for most drones, even without changing any parameters. And then you can still, if you want, you can still fine tune it by hand or with other methods. So basically, the total cost also for that is that you need to first develop the whole algorithm. That will take some time, but for Pix4, it's really cool because you have a lot of different drones with the same software. So once you develop that algorithm, you can just reuse it on all of them. All right. So now between auto-tuning and adaptive control. So that auto-tuning that we develop here at Auterion comes from adaptive control. And on adaptive control, you have 2 main ways of doing it. So you have the direct adaptive control, which is here. You have, again, our control loop. You have vehicle dynamics here. You have the control you can adjust. And basically what you do is that you have some reference dynamics. That's what you expect the closed loop system how to behave. And then you have some adaptation mechanism here that will try to make the real behavior match the reference dynamic. It could be kind of a bit black box for you, but basically it tries to do what you expect from him and will adjust in real time the gain of the control to try to match that. There's one famous implementation, his MRAC, that was developed, that is one strategy that works quite well, but it's mostly just suitable for adaptive control and not for auto-tuning. So for auto-tuning, what we choose is more indirect adaptive control. So it's on 2 steps. So you have the first step, which is model estimation. So basically what you do is that you estimate the dynamic of the system by taking a parametric model. In our case, you try to fit some parameters, and then once you get the model, the discrete time model of the system, you can use different controller design algorithm and then tune the controller based on some desired performance here, and then you can adjust the controller. So if it just runs all the time, it will be an adaptive controller. And here, the difference from adaptive control to auto-tuning is basically you engage the adaptive controller at some point when you want to tune the controller, and then you just disengage it such that you have fixed gains. And once you're happy with it, the behavior won't change. Because that's, you have to know, it's a drawback a bit on adaptive control, is that it will vary over time, and you're never really sure how it will behave a bit later, if it will start to diverge, or if it stay converge, or it will change like that. So with auto-tuning, we just run it once, and once you're happy with the performance, you just cut the adaptation part, and you'll be fixed with some parameter, and you know what you have, and you know that it's safe to fly for your customers as well. So here's the overall diagram for the strategy we use for PX4. So here again, that angular rate control loop, vehicle dynamics, the gyroscope measure, feedback loop, our PID controller here, and the attitude loop. And then what we built on top is, here's that system identification part. So what you see is on the left side, you will take so you always need to perform the full identification in closed loop, because otherwise the drone cannot fly. So what you will do is to take the output of the control, which will be the torques that you want to apply to the drone, and then on the output you also take what's the angular rate currently of the drone. So you will start to inject some signal into the drone to excite the dynamics, and then you will do a curve fitting in the center here to try to fit the parameters on your discrete time model that you want to use. And then to make it work all together, you need a supervisor that has some high-level logic state machine to tell you, I want to tune roll, I want to tune pitch, I want to tune yaw. It will also check the different gains that are obtained. It will check the model if it makes sense. And then it will, with some controller logic here, it will design the gains for your both your rate controller and your attitude controller here. So what we use here, because it runs on the autopilot directly, so we need to use lightweight and safe algorithm. So in the sense that if you want to use optimization, it's much safer to use something that is linear than nonlinear to avoid being in a local minimum, for example. And you need to have something that can run in real time, so fast. You don't want to have huge metrics inversion or anything that is super expensive to run. You need to run fast, you need to run on the drone in real time. And we choose to use a fixed structure. So we have a defined model with some parameter. We have 4 parameters to identify, and then we'll do the curve fit on that. Also for the controller design, we try to find a law that has a closed form solution, so we can compute most of the algorithm offline, and then we can just re-implement the equations that will give us the result directly on the controllers, on the FMU, so on the autopilot. So first, to develop the algorithm and to try to optimize them, we first developed a Python script here. So it's a GUI that takes as the input a log file that you got from your flight. So we've been outside with several drones, gather a lot of data, then we've been able to process them through that tool, and it will actually run the identification, estimate the model here. So you see how the parameter converge. Also, that's in discrete time, the result you get. So you said your poles, your zero. You can see if they make sense. Then you can simply replay the data. So you take what's the input of the system, you replay them through your model, and you see here if they really match your measured output. So you can basically check if how the parameter estimation is, so its performance, and then also like the implementation of the controller directly. So we're able to replay with the model the controller that was designed from some high-level criteria, and then output, for example, here the step response, also get some frequency response of the closed-loop system. And there were some sliders on the bottom to try to find what are the good meta parameters to define the response of the algorithm. So here we were able to change the rise time, the desired rise time, also the damping index of the step response, and some other parameters, and it will directly show up here also the gains of your controller. And if you're not happy with the performance, you can also just slide them to see how it goes and try to find better meta parameters for the algorithm. So that's how we first developed it. So it was not directly adding on the drone and see how it goes, but first gather data, do it offline, but implement everything as if it will be online. So for example, we run a recursively square. So it was also running directly the recursively square on the Python script, and use all the same implementation. And once everything was done and we were happy with the results, we started to implement it on Pix4 directly. And that's the part that is a bit higher level. So that's the state machine we had to implement. So it goes really step by step. It has to initialize some filters. It needs then to identify the roll, the pitch, the yaw axis dynamics. Then it will compute the new gains. It will apply them, try if they are good. So we just save also the previous parameters. We apply them, we apply some inputs, see how it goes. And if it goes well, we can keep them. If it doesn't go well, we'll immediately revert them and notify the user that something is not good. And then you can always extract the log file, replay them through the Python script to see where it could be improved. And to make sure that the implementation also is correct in Pix4, what we did is to make some unit tests, both on the Python script and in the implementation in C++ in Pix4, and make sure that the outputs are the same for the same inputs. So then we're sure that we both have on both sides we have the same algorithm exactly, and we don't have numerical issues or mistake like that. So it's fully covered by unit tests as well. Here is one log of flight test results. So we're using a X500 quadcopter, which is 500 millimeter size. It's a quadcopter. It's kind of lightweight, quite rigid, so it worked really well with the auto tuning on that one. And you can see here, those are the parameters of the model. As I said, we have 2 poles and 2 zeros that we want to estimate, and so that gives us 4 parameters here. And you identify the roll, the pitch, and the yaw axis, and you see how fast it converges. So really, it only takes a couple of seconds to converge to the final parameters. What's on the right side, for example, we have also the variance of each parameter. So to see the convergence. Bottom left here, you can see the controller gains, how they are also directly designed in real time. So at every step when we estimate the parameters, we also can just compute the parameters of the controller, because that's super quick to compute. It's as I say, it's a closed form solution, so you just need to run a few multiplications and additions, and you get the result. And that's basically the gain it found. It's really soon stable, and that's on the bottom right side. It's the state machine that increment through the whole procedure of tuning, and at the end you have your drone that can fly with its new gains. Then they are saved in the parameters. You can change them slightly if you want to have some other behavior, but that's basically how it works. Quickly, so to conclude that, so we have on one side benefits and the limitation of that whole auto-tuning. So it speeds up a lot the initial bring up of a new drone. So usually if you're lucky and you have a drone that is exactly the same size as other ones and with the same propulsion system, you can use default gains. Most of the time it kind of works, you don't get super good performance. If not, you can use then the auto-tuning that will adjust it for your drone, and that usually works well. And you don't need to have extra knowledge, you don't need to iterate a lot on it. So it's really, you go in QGC, you click on the auto-tune button. We also made the whole integration in QGC. So you click on it, you see the status, it will do it for you, it will tell you if it succeeds. If it fails, what's happening, and then it will apply the gains for you. You don't need any control theory to have it working. And you also get out of it like a dynamic model that you can use if you want to do the tuning offline. So if you want to perform any PID control design offline, you can already use that model and then do the rest in MATLAB, for example, or Python. The limitations that we have some meta parameters that you can set. So that's usually quite understandable, like rise time or damping of the closed loop response. But those might not be exactly the same. For example, if you have a small drone or a super large one, so if you have a tiny racer or a large VTOL plane, you might need to adjust them. So you cannot just click on it and expect to work for the whole range of drone of all size. So you still need to have one or two parameters that you need to change by hand that are much better understandable than PID gains, but you still have to do it. Also, you need to be able to fly the drone before performing the auto-tuning, because you need to be in flight, you need to be stable while doing the auto-tuning. The strategy to do it, also to do the identification that properly, we inject a signal to the controllers to disturb it. So the drone needs to fly already in a stable fashion before you can perform the auto-tuning. You cannot tune it from the ground or from without flying. Also, we have a fixed model structure, which means that I say like 2 ball to zeros. That works properly for rigid frames, so all the multicopter, it's fine. Most of VTOL planes, they are fine. But if you have some complex dynamics, a lot of flex in the wings or in the body, you have extra modes of resonance, then you can have a degradation of the identification, and then you can get a worse result out of it. And the most important one is that it doesn't unfortunately fix your hardware problem. So if you have a lot of vibrations, maybe the resulting control will be too aggressive for you, so you will see some vibrations. It cannot deal, for example, with huge delay. So if you have a lot of delay in your control loop, that won't fix it. It will try to do its best to reduce the gain, to have it flying, but it won't fix everything. But it should give you a good base tuning for most platforms. All right, so now question time. I'll check the QA. So first one is the first one is down. So in direct adaptive control, how do we define the reference dynamic? In what term? So in direct adaptive control, that's I can maybe show quickly the slide so everyone can understand. So it's that one on the left side. The reference dynamic is normally you define just a transfer function, and that will give you the response of the vehicle. So it's, for example, it can be just a low pass filter that you define, and that's how you want it to behave. So you can basically define rise time, overshoot, bandwidth, or things like that, and that's how you want the closed-loop system to behave. And then the adaptation mechanism will try to match that with your real response. Second one, what's the role of the model estimation block? So it's just to provide you a mathematical model, then to create the PID controller gains. So to do that, you need to have a set of parameters for the when you estimate, you get your discrete time model, and from those different coefficients, you can put them in an algorithm that will generate for you the PID gains. So that's why you need to build first the model in case indirect adaptive control. You first need to build a model to know what you have to tune in a mathematical sense, and then you can design the controller from how do we initialize the covariance for a recursive least square estimator? Usually you can initialize them to a large value, and if it's in our case it's a linear regression problem, so you can initialize them all with some large value, and they will collapse properly. You need to make sure that you have good signal conditioning from the input, the output. You have the same scale, roughly, and in a way you don't need to do anything crazy for the initialization of the covariances. Is the Python prototype tuning program available for use? Yes, so absolutely. Now it's on a private repository, but I will upstream everything. So the peaks for auto tuning, and alongside I will upstream the Python script as well. So you can also use it to do your own tests. You can implement your own identification or controllers design. So you will be able to use it as well. Everything will be open source. You can contribute to it if you want. Does the auto-tuning will tune for both manual flight mode and position flight mode? That's not at the moment. So for now, we'll just tune with that one. It will tune the inner loops, so the rate controller, the attitude controller. It will not tune the velocity and position controller yet. That will be a follow-up project that we'll probably do as well. Can auto-tuning be engaged before takeoff? No, it's during flight, so you need to fly to identify the model. What kind of dynamic model does it provide? So it's two-pole, 2-0, one-time delay parametric model. It's in discrete time. And if you want more details, I mean, you can reach out to me to Slack also. How is the closed form computed for PID controller? Is based on pole placement of design. So it's there. It's called GMVC. It stands for Generalized Minimum Variance Control. So that's also, you have a reference model, and it's an optimization to minimize the variance between the output of the the model and what you will get for your closed loop system. So it's an optimization that has a closed form solution, especially in our case because we have a fixed set of parameters that match properly. And from that GMVC controller, you get normally some polynomial controller, and with some tweaks, we can approximate a PID controller. That's how we can extract those PID gains. Do we still have time? Is Autotuner accessible in QGC? Yes, so it will be in the tuning page. So you have like parameter, safety, tuning, and you will have a button for the auto tune. You can click on it. That will also come with the PR I'll make. When will it be available? That's a good question. It will be in the following month. I just need to do the PR and make sure that it works properly for you as well. Do some further tests upstream. So it will be not in 1.12, but it will be in 1.13 on Pix4. That's for sure. That's for sure. Does it work for fixed wing VTOL planes? Yes. So we've made quite a few tests also on for fixed wing vehicles. It's the same approach. It just like the PID design is mostly the same. Also, there are a few differences, but there is one module that makes in Pix4. There is one module for fixed wing side, one module for multicopter. They both use most of the same parts, so the same identification part. The GMVC law is the same also, and there are just minor changes, but it does work for fixed wing as well. For VTOL plane, as I say, it works for most VTOL planes, except if there are if they have large different modes in addition that are not modeled. That cannot be modeled by that parametric model. Control location block. Can you explain the control location block? Control location because it's basically, so it takes the output of the controller, which is the desired torques, and then convert it to motor outputs. So motor, that's what you need to send to the motors. That's basically just a translation. Use a control location matrix for it. Difference between direct and indirect adaptive control. So direct, you have no model identification. It's just a black box that takes everything, change the parameter. Indirect, you first identify, then do the controller. That's the major difference. Yeah, so for fixed wing, what you need to do is to fly at trim airspeed. So then you get the correct tuning for trim airspeed. Then you have to define what's the max airspeed, the min airspeed, and we already have in there the scaling for the airspeed. At the moment, it's not. The control will not adjust directly for flaps, just like the flaps will define the trim, but the control gains themselves, they won't change for trim settings. All right, I think I didn't miss any. So if you have more questions, just reach out to me on Slack, and I'll be pleased to answer those questions. And hopefully you like the presentation and you will like to use the auto tuning. Thank you. Bye-bye.